I should have said this as well on the previous video, but this is basically what I already said. But I just got reminded that I probably talked for too long, so I cut it there. But this one should be in the previous video. Okay, let's go on. But everything here I said, I said in the last video. So let's move on. First, modern compilers, that means compilers that use SSA form, they represent the function, one function at a time. Well, there can, of course, there is a set of functions, and there can also be a graph saying which function calls which, but optimization is usually done on one function at a time. And this representation is called SSA form. And SSA form was invented at IBM Research north of New York. And it is actually at the same lab which invented RISC processors. I mean the Power and IBM 801. Okay. And I should also say that IBM is the primary inventor in optimizing compilers. They have done they have done most of the things. Silicon Graphics is the second best. Well, now they hardly exist, but the compiler still exists as an open source project. Okay, never mind. So, in this SSA form, a variable is only assigned once. So that is static single assignment, one unique instruction. Okay, and the assignment is that A, and static means in the code if you look at it, but not when you run it, because if there is an assignment in a loop, of course it will be assigned every iteration. Okay, SSA form was invented at under several years, more and better. I mean, how to do this algorithm efficiently in the late 80s. And before that, optimizing compilers were not so efficient. And with SSA form, it's very fascinating because you actually understand optimization opportunities better than doing with the previous formulation. So this is really nice. And basically all compilers do that, including the Java virtual machine. For optimization, I mean just-in-time compilation. It translates the Java bytecode into something that is suitable to optimize on SSA form. That is, forgetting about the stack machine and instead have something which is more similar to RISC actually. Okay, so if we translate this to SSA form, the code that we saw before, then what we said is that there can only be one assignment to each variable. And well, there were multiple, so how can we do that? Well, the simple thing is that we simply say, that was a lot of simple, but what we do is to create a new variable at each assignment. So we say A0, that's a different variable from A1. And by doing so, there is only one assignment. Okay, that sounds like a very trivial trick, but it's not so trivial. Well, the first thing, which is not very difficult, is to make sure that we use the correct version of, we should use the most recent version that we, for instance here, we should use A0 since since we assigned it there, and there we should use A1. Okay, but the problem is here. What should we do? I have indicated that we should use a new version, and the reason for that is we don't know which version it is. It's either A1 if we go there, I mean from there, or A0 if we come from here. Okay, and what this is, it's A2 is assigned to a phi operator with A0 and A1 as operands. And what this phi operator does is to select based on the edge that the program uses. It selects the proper version of the variable. Okay, so this is called the phi function, and this is the translated program to use phi functions. Okay, and what is important now is that a definition in SSA form dominates all the uses, so we can be sure that we get the correct value, and there is no risk that we get use a value that we have not defined already. And we can also know exactly which definition that we use, since there can only be one definition. Okay, a simple example of how this can be exploited. Sometimes we write copy statements in the source code. Maybe we don't use variable names like that, but say we just write A is copied from B. If you don't know about optimizing compilers, you may think that this results in a wasted clock cycle. Usually it does not. Such copy statements, they are typically optimized away. So if the code becomes more readable, well, use it, because they won't result in machine code. And how come? Well, this is not always, of course, but I will illustrate what can happen. Okay, so now I have used variable names that reflect the names on SSA form. And what we see here is that x0 is defined there, and now we copy x0 into y0 there. And then we use y0. Okay, so can we, without looking either there or there, just change y0 to use x0 instead? Isn't there a risk that there is a y0 here? I mean a modification to y0 or a modification to x0? No, there cannot be, because there can only be one assignment to each variable, and therefore it must be the same value that was read there, since x0 cannot change, and therefore we can use x0 there without looking for such modifications to these variables. Okay, so this is just an example to illustrate that SSA form simplifies optimizing code. And let's look at another optimization, namely constant propagation. What it does is to try to evaluate constants as much as possible and simplify the code. This can be used, for instance, if we call a function with a constant parameter, and then the compiler can duplicate this function. It's called cloning, and use the constant parameter I mean, it will be a constant then, and try to simplify the code based on that. In this instance, in this call, we know the value of a parameter. Okay, So how can this be optimized? Actually, this algorithm was invented by this person, 1973, and the idea is that if a variable has only a constant, I mean an assignment that is constant, then we know it's constant. But if the variable has different assignments, I mean with different constants or unknown variables, then they cannot, that variable cannot be constant. But what is done with SSA form sorry, is to interpret the program so that the program, the compiler starts it in the start vertex and then interprets it and checks, okay, A is less than B since they have these constants. Okay, so then we can say that C1 is a known constant. Now we have a phi function, and what do we know about it? Well, what we know is that C1 certainly can have a value, but C2 in this, I mean the edge in the control flow graph that corresponds to this operand has not yet been thought of being executable, because this interpretation has never been here. So what we can do is we can skip this operand since we don't think it will be executed. Our view of that may change during later analysis. Well, not in this code example, but if there was a loop, for instance, around all this. But since we can skip this operand, we can skip phi operands if the corresponding branch, okay, the control flow graph looks like this. And here we have the phi, and we interpret, say we say it goes like this, and we have not marked this edge as being executable, so we can ignore this operand and think that C3 will be the value of this operand, C1, so we can conclude that we should print 3 here. And this optimization is really useful to simplify code. Okay, so that is what I said.